Later we'll have it posted. Okay, today we're going to start talking about randomization, and I'm going to use this solar power activity to talk about randomization. So I've asked students on eClass right here, or on the live chat, to go ahead and pick themselves 5 of these. And now I'm going to pick 5. So I'm going to pick, let's say I pick 82. Okay, here, I'll pick 82, 72, 74, and 66. And I got to pick one more. Let's pick 58. And now I'll pick 5. You good with that?
Yes.
So now I can add up. I've got 4 here, so I can put down a 4. Plus, here, let me get my pen over here working. Start this part over here. I just came off a live chat for an hour with AP Stat, so I wasn't quite together here for you guys. I'm sorry. So let's see. I picked 82, right? So that's 1, 2, 3, 4, 5 times 3 is 15. Plus 4. Plus, what's that? 5 times 5. Is that right? 1, 2, 3, 4, 5. That's 25. I've got 1, 2, 3, 4, 5. And I've got 1, 2. Is that 6 times 3? Let's see. 1, 2, 3, 4, 5. 6 times 3 is 18. Do y'all agree with that?
Yes.
Mm-hmm.
Okay. So now I would divide that to find the average. I would divide that by 5. So if you want to pick your graphing calculator or your calculator. By the way, do you guys know how to download the graphing calculators?
No, I just go on a separate tab and use a graphing I use Desmo as a graphing calculator.
Okay, that works fine. Just so you know, in eClass, we put all of the teachers, we put up this Wabbit. You can get this on your computer. And there's also, Ms. Kendry and Ms. McLeod found yesterday that TI is offering it for free. There's a module on our eClass page called Wabbit, and it explains both methods. If you want to download this one, or I'll show you the other one. They're pretty cool. I downloaded this one just a little while ago, the TI. Oh, nope, I didn't finish downloading it. Sorry. I didn't finish. Anyway, but on eClass, you'll see, like on my page, I've got it. Bear with me. You'll see a Wabbit EMU module. It is located right here. And it has the instructions for option 1 is the free TI. They're giving out for 6 months. But when I went and installed it, it only gave me an option to choose the 90-day option. But either way, it's free now. Or the Wabbit EMU, which is this one I'm using right here. Either one. And this one will stay on your computer forever. That one won't go away. So if you want those, just find that Wabbit EMU module on your teacher page and open it up, and you can follow the steps. Option 1, option 2, follow the steps, and then there are links down here to use to get this stuff. Okay. All right. So that's getting your graphing calculator on your computer. So back to our lesson. So I've picked, and I'm going to calculate my mean. So I put in the calculator. There's a couple ways we can do it. I'm going to do it the way we taught about a week or so ago. I'm going to go to Stat. I'm going to go into Edit. And I'm going to enter this data in list 1. So that's 1, 5 plus 4 plus 25 plus 5 plus 18. So there are my 18 pieces of data listed in my list, or my 5 pieces of data. Correct?
Yes.
There's a way I can get a mean, a standard deviation, and a 5-number summary for data that we learned about last week or so. And if I hit Stat and scroll over to Calculate, I'm going to go to the right arrow one time. And I use this one variable stat. The first thing I hit Enter, and I hit Enter again. My data's in list 1, so I'm using list 1. If you put it in a different list, see above the 1 button, the 2 button, the 3 button, the blue L1, L2, L3, L4, L5, and all that. If you hit the second button, you can change the list. So you could put multiple lists of data in if you had to do this a bunch of times. Now I tell it to calculate. In X bar, that is the mean. The mean of this that I chose, X bar, equals 13. I'm trying to do this with my mouse instead of the pen. Or get the pen. All right. Whoops. Whoops. Sorry, guys. Big eraser. X bar equaled 13.5. Okay. Now, the whole thing I want to talk to you about with this, the big idea, the way we just picked in statistics was not truly random. That is not what the definition of random means. I went through and picked, but the word random in statistics has a very, very, very specific definition. And it means that the entire population had an equal probability of being chosen. Well, as a human, I cannot choose randomly. Let me tell you something. Guess what never got chosen? Doesn't have to, but I just chose from kind of the upper half because that was closer to me. So I didn't really choose randomly. None of these ones down here had a chance of being chosen since I just chose like this. All right. And you kind of chose the same way. Your random selection, whatever your sample is, was not truly a random sample. To have so that every one of these 100 different rectangles can have an equal probability of being chosen, the way we need to do it is to use a random number generator or a calculator or a computer that can choose randomly. And I'm going to teach you how to do this with this calculator. And if the other calculator gets set up, I'll show you another way to do simulations with it if we have time. But here's what I'm going to do. You see this math button, the third button down on the left. I'm going to choose math. And I'm going to scroll over to PRB. I'm going to take a shortcut. I'm going to go left one time instead of right 3 times. So I'm at the probability. And you see where it says rand right here? That is not the feature we're going to use. We're going to go down to this random integer feature right here. Okay. However, there's also another one I want to talk to you about. If I scroll down past this, down below, there's a random integer no repeat. Well, let me ask you a question. Out of this sample, would I want to pick number 82 here and number 82 again a second time? Would that be kind of a good way to find an average? What if I came up with 82, 82, 82, 82, and 82, my whole sample were sample sizes of 15?
No.
It was the same. So that wouldn't be good. So maybe out of this population.
What are the odds of that happening?
Do what? What was that?
The odds of that happening are really, really slim.
They are slim. They are. But you know what? What's the probability that 82 gets chosen? If I took numbers 1 through 100 and put in a bag and I chose out an 82, what's the probability that number got chosen? It was 1 out of 100. Is that right?
Mm-hmm.
Well, guess what? If I put that number back in the bag, what's the probability it gets chosen the second time? 1 out of 100 again. Same probability as before, right? Well, I really don't want to have that one in there twice, so I'm going to use the no repeat. You with me? So I'm going to choose number 8, and here's what I'm going to do. I'm going to tell it choose numbers 1 through 100, and here's the comma right above the 7 here, comma 100. And I'm going to close the parenthesis, and what I'm going to do now is I'm going to hit enter, and it's going to randomly choose. And it put these numbers in order 1 to 100 in just some random order. You with me? So my sample that I would choose would be number 10, which there's number 10 right there. Okay. Number 31, number 22, number 37, number 87. So 31. So you see how I just chose randomly? I let the computer do it for me, and I'm taking what it gave me. And did every one of these have an equal opportunity of being chosen by doing it with all 100 numbers in a system where each one of them had an equal probability of being selected? Was that a good way of choosing? That's what the word random in statistics specifically means. Everything in the population, every one of these 100 rectangles had an equal probability of being chosen to be in my sample of 5. Okay. So there's the 22. Oh, there's another one. There's a 37. Let's see, 37. Right there, and 87. So up here, 87. So there would be my random sample. That is called a simple, the method I just used is called a simple random sample. And what was so important about that? Every one of these rectangles in my entire population had an equal probability of being chosen because I put numbers 1 through 100 in my number generator, my random number generator, and had it line them up in order. And the first 5 it picked for me, that's my sample. Guess what I would do if I want a second sample of this population? Well, if I want to choose a second sample size of 5, I can simply go second, enter. I'm using this entry button. Look what it brings up. It brings up my same entry I put in and hit enter. And there's a second sample of size 5. You with me? If I wanted
Yeah.
a sample of 6, I would just scroll over until I got a sample of 6 or 7 or 8. But did every one of those have an equal probability of being chosen in the second sample? They did. So the idea of random in statistics is the idea that everything in an entire population has an equal probability of being chosen. The only way we can really do that is if you make a numbered list and put that numbered list into a random number generator and let it choose the random numbers for you. Okay? So on a quiz or a test, if you're asked what's the best way to choose a sample, what's the best way to choose a sample in statistics? What's the best way to choose a sample in statistics?
To pick 5 and divide
Random.
by it?
What? I just heard it.
Randomly.
Randomly. Does randomly mean there? Is this a random sample? That one, that one, that one, and that one.
No.
Did I just do a random sample?
No.
No.
No. What does a random sample mean to do?
Random sample is making sure that all samples have an equal probability of being chosen.
Everything in the population. So there's 1 through 100 in my population. There's the population. There's 5 samples. The 5 that I chose was my sample. Okay. So a simple random sample is taking an entire population, numbering it, putting it in some random number generator, and choosing the size sample you want from that randomly selected list of numbers. Okay? So then I would take a 1 plus a 1 plus a 4 plus a 4 plus a 4, and I would add those up and divide by 5, and that would be my random sample. Okay? All right. So that's the definition of random in statistics. If you're ever asked a question in statistics about what's the best method for collecting a sample, the answer is a random sample. You must choose randomly, and random doesn't mean you picking the best 5 you like or the closest 5 to you. Could I have picked what if I was picking my random sample, if I did that? Because that was easy. That's called a convenient sample, and that's not really the best way to choose a sample. All these others up here didn't have a chance of being chosen. So the definition, this was a vocabulary lesson. The definition of random in statistics means that every item in your population has an equal probability to be chosen to be in your sample, whatever size it is. It could be a sample of 5, 6, 10, 20, 100, whatever it is. So if I had a book full of these pages, are you with me?
Yes.
I may randomly choose 15 pages. So this book, if it's got, I don't know, let me just, I'm guessing, but let's say this book has 692 pages. Say this book has 692 pages in it. I may put 692, 1 through 692 in my random number generator and choose 5 pages from the book. And from the 5 pages, I may take those averages. Okay, or I may pick 15 of the rectangles from each of the 5 pages. I've kind of done some different sampling methods there. I've done some what we call cluster samples, but it's still choosing randomly where everything in the population has equal chance of being chosen. If I randomly chose 15 of these or 5 of these 692 pages, did every page in this book have an equal opportunity to be chosen?
Yes.
Okay, and so if every page has an equal probability of being chosen, does every rectangle that looks like the ones on the sheet, does every one of those rectangles have an equal probability of being chosen?
Yes.
Okay, random sample. Everything in the population has an equal probability of being chosen to be in the sample. Okay, vocabulary. That's all that was. All right. How are we doing so far?
Good.
Good. Okay. All right. So the next thing we want to talk about from AKS, hang on. All right, AKS 26. Let's see, did I miss something, Miss McLeod or Miss Kendra? Did I miss something from AKS 25 we definitely need to cover? Oh, let's talk about why we randomize real quick. This is a brief explanation, and it's not something you really need to know big time right now. If you were taking AP Stat, this would be a fundamental idea that you would understand. But right now, in the scope of the Algebra 2 statistics we're learning, the reason we randomize is because in this lesson right here, what my goal was to find the average size of all of these 100 rectangles. But I didn't want to add everyone. I didn't want to add up a 1 plus a 1 plus a 1 plus a 1 plus a whatever that is, a 12 or whatever it is. Okay, I didn't want to add all those 100 numbers up and divide by 100. That was a lot of work. So I wanted a really good estimate. Well, my sample that I select, my sample that I choose, needs to be able to represent the population I want to estimate. So by randomly choosing from a population a small sample of some sort, some sample size, that sample, when you find its average, should be able to be generalized to the entire population. It should be a good estimate for the whole population. So the reason we randomize is so that we can generalize. Does that make sense?
Yes.
From these five rectangles that I took and averaged them, I believe that my average of 13.5 is a good estimate if I were to add all 100 of these up and divide by 100. I believe that's a good estimate because I chose a random sample. I can generalize this estimate to the entire population. That's why we do it. Okay? That's the purpose. Okay. Let's see. That's today's lesson. Okay, so this was AKS 25 also. It says a reporter wants to know how people feel about the governor of her state. She decides to ask 100 people their opinion and think of several ways to ask the 100 people. For each method, explain the benefits and drawbacks, then choose the method for selecting 100 people that would be the best represent all the people in the state. So from 100 people that she asked a random sample, a small sample, she's going to estimate what all people in the state might say on average. Okay. So you go to the capital city and find 100 people interested in politics to respond to the survey. That's one method. You ask the 100 most politically influential people in the state to respond to the survey. You obtain census data for the state and select 100 people from the list to survey using a random process. Do y'all know what a census is, guys?
No.
A census, we just did our U.S. census this year. The U.S. government sends out a questionnaire to every household in the United States. And you have to fill out information about your household and respond back. Well, the states get that information about people from their state. So wouldn't that be information from everyone in the state?
Yes.
Then they randomly choose 100 people from that census to send them the survey. And then we're going to ask 50 registered voters who voted for the governor and 50 registered voters who did not vote for the governor to respond to the survey. So this is about how we're collecting the data. This goes right along with the last. If you think about what we did here, think about these different methods that are going on here. Which one of these four methods do you think might be the best method to use? 1, 2, or 3? You think method 1, 2, or 3 would be the best to use? Or 4. Sorry, 1, 2, 3, or 4.
The third one.
The third one? And why do we think the third one? Because everyone in the state had an equal probability of being chosen to be in the 100, because what do? They took the census information from everybody and
then did it randomly.
And they chose randomly from everyone in the state, 100 people. So that this sample should be more representative of the entire population of people than any of these other 3 methods. This method, what they did is this called clustering, or you can call it, well, no, I'm sorry, they didn't cluster, they stratified. They put people into 2 groups, either people that voted for the governor or people that didn't vote for the governor, registered voters, and then chose 50 from each group. That's called a stratified sample. It's a way of grouping. A cluster sample is another way to group. This is just vocabulary and how to collect data. And then they asked the 100 most politically influential people, what do you think about the 100 most politically influential people in the state? Are they going to have the same opinions as people that don't care about politics?
No.
So their surveys are all going to sound pretty much the same, but would that be a good representation of the entire population of the state?
No.
No. And they go to the capital city. Well, does everyone live in a city life, that like in Atlanta, that is going to be representing the state of Georgia? If you only ask city people, would that be a good representation of an entire state?
No.
Okay, so you see, there's reasons why those are examples of why randomization, Now, let me ask you this. Could they get 100 people? Could they get a majority of the people that live in the city of Atlanta and still did it this way? Could that sample look like that?
Yes.
It could happen. But typically what they do is they'll get a sample of 100 and then get another sample of 100 and another sample of 100, and then maybe take those 3 different samples and average those. So then there's not one sample that's big influenced by one thing. Okay? All right. But we don't need to get into all that. The idea is that you understand that this is the best method because they're giving everyone an equal probability in the state of being chosen, and they're randomly choosing the 100 people. Okay? So that's what the word random means. And the reason we do it is so you can generalize what you find from the sample. So these 100 people that are asked here would be the best method to generalize to the entire state. If you want to say, we believe people in the state of Georgia feel this way, this would be the best group that we chose of the 4 methods to use that to talk about the entire state, to generalize. Okay?
All right.
All right. So now, AKS 26. Let's get there. Twice AKS 26. All right. So this is about doing simulation. I'm trying to remember on the quiz. Miss Kendry and Miss McLeod, are y'all still there?
Yeah. Yes, we are.
On the quiz, did students actually have to use a random generator to choose randomly?
No. They are calculating. Are you hearing me?
Yes.
Okay. It's about calculating really probability. Some of the problems, or at least one problem, has to calculate probabilities.
Oh, yes, that's right.
Yeah. And
Okay.
Actually just looking at the sample and deciding if it's consistent with the population or not. I mean, if what we see in the sample, what we decide or conclude about the sample will be consistent about the.
Okay, so there's vocabulary we need to touch on real quick, guys, that you need to understand. When you're going to see the word, would the sample that I chose here, I use the word represent or be able to generalize to the population. But another question is, would it be consistent? Would this sample be consistent with this population? Well, if this average is pretty close to the true average, then it would be considered consistent. That's what the vocabulary is. So when you see the word consistent, it's really talking about, did we collect a random sample, and did my random sample fairly well match what the overall population is? And they should be fairly close. Would you agree with that?
Yes.
If I collected this sample, look at this. If I collected, forget about this one. Well, even this sample, if I average this 1 plus 1 plus 1 plus 1 plus whatever that is, 12, would that be a good way? Do you think that would be a good representative or consistent with this population's average? Do you think that's going to even get close to an average of 13 or 14 or 15 or 12 or 10?
No.
No, because if you take this 12 and add 1 plus 1 plus 1 plus 1 and divide it by 5, is that 12? Let's see. Let me blow this up just again. We'll just check it real quick. We'll look at this. All right, so that is 1, 2, 3, 5, 6. That's 12. So look at this. If I took, oops, clear that. I took 12 plus 1 plus 1 plus 1 plus 1. There's my sample of 5. Hit enter. Divide that by 5. Do you think 3.2, do you think the average of this population is anywhere near 3.2?
No.
No, because there's some pretty big ones. So the average is going to be somewhere between 1 and, you see the big ones here. This is like, what, 16, and I think there's some 20 ones in here. So I would think the average is somewhere between 1 and 20 and closer to 10 to 12 to 13 than it certainly is to 3. Wouldn't you agree?
Yeah.
Okay. So this sample would not be consistent with this population. And the reason it's not, I didn't choose it randomly. I just picked the first 5. Okay?
Okay. So, Mr. Jones?
Yes.
Okay, another type of problem on the quiz. It's about So we calculate something about a sample, we get to a conclusion, and then we predict what happens with the population based on how the sample behaves.
Right, the inference. Okay, so the inference phase
And
here.
how do you, it's a calculation of proportions. So this is what I would do, what I see here in the problems, because I'm actually giving you input from the questions in the quiz. Yeah.
Okay, and yeah, I looked at it this morning, but then I had an AP Stat chat before this, and I was getting ready for AP Stat. Anyway, my mind kind of went away from Algebra 2, and then it ended and this started. I didn't have time to really prepare, so I apologize to you guys for that.
No, but that's the idea of another type of problems. And then please touch the difference between experimental probability and theoretical probability.
Okay, very good. Let's do that. All right, we'll touch on that first, and then I'll try to find examples. So in AKS 26, I'm trying to.
I'm suggesting exactly. Really, let's give examples of spinor. So on the quiz is a spinor presented, and now you can choose whatever you want with the spinor.
No, I'm going to use rolling a dice, similar to a spinner or flipping a coin. I'll talk about flipping a coin and rolling a dice. Okay. All right. So guys, let's talk about probability. The vocabulary terms. There are two vocabulary terms I want to talk about. Let's see, this is not what we want. The vocabulary terms are going to be theoretical. Let me get a place to write here. Excuse me. I'm just gonna use this sheet of paper to write on. This has nothing to do with that example. All right. So theoretical probability versus experimental probability. All right.
Yeah.
Oops, it's a B. Smaller. All right. So probability. Very good. Okay, so theoretical probability. What is the probability of flipping a heads on a coin? Can anyone tell me the probability of flipping heads on a coin?
50%.
50%.
Okay, so the probability of heads on a coin equals 50% or 1/2. Would you agree with that?
Yes.
Yes.
Okay, very good. Either one of those, or I can put 0.50. All three of those mean the same thing. Would you agree?
Yes.
Yeah.
We've got our fraction, our ratio, we've got our percentage, and we've got our proportion. Okay. All right. So if I flip a coin 10 times, does that mean I will get exactly 5 heads and exactly 5 tails every time I flip a coin 10 times?
No.
No. Okay. So theoretical probability is the probability that we would expect to happen when flipping a coin. Okay. The experimental probability is a probability that comes from actually doing this. So I'm going to flip a coin using my calculator. I'm going to teach you how to do this. I'm going to flip a coin 10 times. And what I'm going to do, I'm going to use my random number generator. Now, on heads and tails, are they going to be allowed to repeat?
Yes.
If I flip a coin twice, could I get heads and then a head?
Yeah.
Okay,
Yes.
that could happen. So I'm going to flip a coin 10 times, and I'm going to use the one. I'm not going to use the no repeat. I'm going to use the. So it's okay to repeat here. And I'm going to do this. This is my way of doing it. I'm going to let 1 equal heads and 0 equal tails. And the reason I'm doing that is because then I can simply add up my list, and whatever the sum is, that's how many heads I got. Would you agree with that?
Yeah.
So watch what I'm going to do. I'm going to put 1, comma, 0. I'll tell you what, it might not take, it may make me flip it. Here, I'll just flip it here. 0, comma, 1, comma, 10. This app will let me put in how many I want it to do for me and do that. The no repeat, you've got to put all the numbers in and then pick the first numbers, how many you want. So I'm going to have this flip a coin 10 times for me. And I'm going to do something kind of tricky here. You ready for this? I'm going to store it. I'm going to hit this stow button. And I'm going to store it in list second L1. I'm going to store it in list. Whoops, it didn't take list 1. Second L1. I'm doing this for a reason. If I was going to flip a coin 100 times, I wouldn't want to have to add it all up. And I'm going to hit enter. And now if you look, I've got a 0, 0, 0, 0, 1. If 1 is heads, if I keep going across, what did I get? I got 2 heads. I got 2 heads out of 10. Is that right?
Yeah.
Okay. So if I was asked, what is the experimental probability based on this simulation? What is the experimental probability of flipping a heads? My probability is not 50%. My probability, somebody's got some music playing there. Is the phone going off? Is that all right? All right. So my experimental probability is 2 out of 10, or reduce it 1 out of 5, which if you put it in a calculator, 1 divided by 5, it'll show you it's 0.2 or 20%. So you want to put 1 divided by 2 and hit enter. I'm sorry, not 1 divided by 2. 2 divided by 10. Let me clear that. Sorry. 2 divided by 10. If you weren't sure about that, put it in the calculator. It's 20%. So if you were asked on a quiz or a test, what is the theoretical probability of flipping a coin or getting a heads if you flip it 10 times? What's the probability of getting a heads? It's 1/2. Then it shows, what if it shows you a chart and says, Mr. Jones flipped a coin 10 times, and these are the results. What is the theoretical probability of flipping a heads? Well, that's still 50%, but what is the theoretical probability of flipping a heads? It is actually the result that you got from the simulation, from doing it that many times. So from this simulation, the experimental probability of flipping a heads is 20% or 1/5. Does that make sense?
Yes.
So what's the theoretical probability? What's the probability when you roll a dice? What's the theoretical probability of getting a 2?
1 out of 6.
Okay, 1 out of 6. Okay. Now, what if I flip a coin, or what if I roll a dice 6 times? I would expect to get 1, 2 out of 6 rolls. Would you agree with that?
Yes.
But let's find out what an experimental probability might be, and it changes every time. An experimental probability, here's how I would do it in the simulator. I'm going to have it choose. Now remember, they can repeat, right? So I'm going to have 1, 6, 1 through 6, and I want it to roll the dice 10 times. So you know what? Let's roll it 6 times. Okay. So I'm going to have 6 rolls of a dice, numbers 1 through 6, and it's going to roll 6 times. And so I've got a 4, a 2, a 5, a 2, a 1, and a 6. What is my experimental probability of rolling a 2 from this?
2 out of 6.
1, 2 out of 6. So the experimental probability of rolling a 2 was 2 out of 6, or 1/3. See the difference?
Yeah.
Theoretical probability is what you would expect to happen. Experimental probability, you got to do something first and find out what happened. And that's what you use. Okay? Difference between theoretical and experimental probability, done. All right. What if you had a spinner that was broken into, I don't know, let's say a bunch of sections. And numbers, let's say, I don't know how many sections, that's 12 sections. What if numbers 1 through 12 are on there? What's the probability of getting a 12?
1 out of 12.
1 out of 12. But then what's the experimental probability of getting a 12? I don't know. I got to spin it, right? So you can't know until you spin it. And whatever result you get from doing the simulation is the experimental probability. So to get an experimental probability, you must run a trial. Okay. Make sense?
Yes.
Okay. All right. And then the last kind of question we want to talk about would be calculating probability, correct?
Yes.
No,
Let's see. Miss Kendra, you still there?
yeah, Mr. Jones. No, predicting. So a sample gives me an answer. Okay. So I'm surveying 100 students at
Okay, I've got it right here. I think I've got it here. You ready?
Right. Yeah. And then you just
all right.
you just multiply by whatever, you know what I mean. We do proportions, yeah, and we get the same answer. I mean, yeah, the sample for the answer for the population, yeah.
Okay, so let me go here. I'm going to erase all this good stuff here. Get rid of it. Make my eraser big. Bear with me. Okay. All right. Let's see. You know what? I wonder if this example would work for us. No, this. All right. Here's a bit of an idea. No, that's not it. That's not it. Let's go back to. I'm trying to remember if there was an example in one of the lessons.
I'm looking too, but it's
I know. I'm sorry, guys. Let's see.
it's not getting us anywhere.
Should be right here. Should be right here.
These are not with calculations. That's a problem.
We might be able to do it with this picture here. All right, guys, let's look at this for a second. Let's be creative and come up with an idea of what might be going on here. I've got one that I don't know. Anyway, let's see. All right, here's my example. Here's what I'm going to say. Here's a population. Let's say these are Algebra 2 students. All right. These are the Algebra 2 students that are going to make an A on the quiz today. You with me?
Mm-hmm.
How many students do we have in a whole population? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 3.
30.
We have 30 students. How many students made an A?
5.
1, 2, 3, 4, 5. So here's what we've got. Let's talk about, I'm going to work both ways with this. So we would say that 5 out of 30, or 1 out of, how many times is 5 going to 30? 6. You with me?
Mm-hmm.
All right. So we would say that 5 out of 30, 1 out of 6 students made an A on the Algebra 2 exam. We're predicting that. All right. So now I want to talk about going backwards here. And by the way, let's do this. I'm just going to do this for you to show you. But if I want to know the proportion, 1 divided by 6 is 0.1667, if you will, equals 0.1667. That's the 6 repeated right there, just rounded to a 7, because the 6 after round that 6 to a 7. Okay. All right. So now let's say that we took a sample, okay, of 30 students. And we took a sample of 30 students, and 0.1667 of those students made an A. You with me?
Mm-hmm.
And now all Algebra 2 students, let's say we have 500 Algebra 2 students at South Gwinnett. All right, this was a sample of 30. By the way, it was a randomly selected sample, okay, guys? I'm telling you it was random, so we randomly chose 30 test scores. We randomly chose 30 test scores from Algebra 2 after the exam. On Monday, all the Algebra 2 teachers got together and put all the scores in a big old computer generator, and we randomly chose 30 scores, and we found that 5 students, or 1.67 students, made an A from the 30 that we chose. Well, based on this sample, how many students do we think in all 500 Algebra 2 students made an A on the quiz? Based on this sample, how would I find out how many of these students made an A? Well, my sample should represent my population. Would you agree?
Yes.
Therefore, the sample proportion should be fairly close to the population proportion. Would you agree with that?
Yes.
So I could use my sample statistic, a number I got from my sample, to estimate the population's parameter. So I could multiply 500 times 0.1667. And if I do that, I take 500 times 0.1667. I should have about 83. And by the way, we always round up on these. I would say that approximately 84 of the 500 students made an A. Is that exactly correct? Do I know that for sure? Do I know that exactly 84 students made an A?
No.
No.
But should that be a pretty good estimate based on the sample that I took, if I took it randomly?
Yes.
This is called inference. This is how we make decisions about populations, okay, from samples. We collect a sample, we find the proportion or the mean of what happened to the sample, and I use that to estimate what would happen in a population. If I want to know how many, I just multiply the sample proportion times the population's total, and it should give me an approximation of the population's total. Okay?
All right.
Did that work, Ms. Kendry? Was that a good example?
Yes, it's a very good example. And actually, may I just say, so in the problem, you are given 5, 30, and 500. So, Mr. Jones, in this top right corner here, in the top right corner, yes, please write 5 over 30. So just read the proportion. If 5 out of 30 have an A, that is equal to question mark. No. It's equal to question mark over 500. So that's your proportion right there.
Right.
It's not 30 over 500. It would be 84 because you calculate it.
That's right. I'm sorry. You're right. 84.
Yeah.
Yep.
So I'm just saying exactly the proportion, which it's 0.1667.
Yes.
5 over 30 is how much over 500. So that's what you have to look in the problem, students, and see the difference.
Divided by 500 is the same as our proportion of 5 divided by 30.
Yeah.
Okay.
And this will be called to predict. So you will be given these two numbers, 5 over 30, related to the sample. How does the sample behave? Then predict how will the population behave.
I use a sample.
Yeah.
To predict.
That's it.
A population.
That's
value. Okay.
We covered it all. You covered it all, Mr. Jones.
Excellent. All right, guys. Are there any other questions for today? Well, and I know we're going to be doing another live chat tomorrow, which I'm sure tomorrow's can cover today's lesson. Today's lesson I like a lot, by the way. It's getting into good stuff. Where it was today's stuff. I'm going to spend, and I don't know if it'll keep recording, how long the recording can last, but I'm going to spend just 2 minutes on margin of error. And then you guys can look at the lesson, see if you can figure it out from there. But I'm just going to spend 2 minutes. All right. So if I was going to estimate, here, I'm going to use what we just did to estimate. If I was going to estimate the true number of students that made an A on the test, we think it's 84. Is that right? But let me ask you a question. What if I created some interval? Remember, I took the number that was 83.35 and rounded up to 84? Would you feel more confident by me saying exactly 84 students made an A on the test? Or what if I created some interval, like a number line, a lower bound and an upper bound, and I said, I think it's somewhere between, I'm going to subtract 4 from this. I'm going to take 84, and I'm going to add and subtract 4. That's going to give me 84 minus 4 is 80. Would you agree with that?
Yes.
84 plus 4 is 88. So what if I said I really think that somewhere between 80 and 88 students of these 500 made an A? What do you feel is going to really truly capture the true number? Do you think 84 is exactly right, or do you think I might have a better chance of being right by creating this interval? By creating an interval, if I told you somewhere between 88 students made an A, do you think I could possibly be right, more right there than exactly 84?
Yes.
Okay, I got a better chance of getting the right number because I got a wider interval. What if I did this? What if I said, and let's say right here, maybe I'm about 80% confident. Right here, I might be about 20% confident that's the exact answer, that single number. Now maybe I'm 80% confident. What happens if I take this number, I'm going to call that a margin of error, and I'm going to make it bigger. What if I say I'm going to take 88 or 84 and add and subtract 10 to it? Now what do I have? I've got an interval that goes from 74 to 94. Is that right?
Yes.
What if I tell you I think the true number of students from that 500 that made an A on the test is somewhere between 74 or 94? Are you more confident that 84 is exactly right, that 80 to 88 really contains the true number, or 74 to 94 contains the true number? Which one do you feel more confident has the real answer of how many of those 500 students really made an A? Do you think my confidence just went up or down by making a bigger interval?
Down.
You think I'm less confident? So you think my interval, look, I'm looking at a number line right here. I'm looking at a number line where I believe 84 is an estimate. And I'm going to go down to 80 and up to 88. And I think the true answer is in here somewhere instead of just this one number. Okay? Now, what if I let somebody else pick an interval and I let them go from 74 all the way up to 94, and they believe the answer is in here? Who do you think has a better chance of actually predicting where the answer is? This person that said 84, this person that says 82 or 80 to 88, or this person that says 74 to 94? Which person do you think has a better chance? Person number 1, person number 2, or person number 3? Which one do you think has a better chance of really obtaining the true number of students that made an A?
The person from 74 to 90.
Oh, the bigger interval gives me a higher confidence. I'm more like 95% confident the true number is in here. So as my interval gets bigger, my confidence grows that I actually have the true value in there somewhere. Is that right?
Yes.
Okay. So that's kind of the lesson. That was today's lesson.
I have a question.
Yes.
Mr. Jones, I have a question, please. So we have here 5. I just want to ask you, because from your experience, I really don't have much experience in statistics. So my question now is like this, as I'm looking at this example. We have 500 students, that's our population, let's say, and
Okay.
30 students is our sample. My question to you, I understand. So as your student today, I do understand the direct correspondence. So direct proportion, yes, it's not inverse proportion, it's direct proportion between margin of error and level of confidence level, okay, confidence level. My level of confidence increases with the margin of error, okay?
Mhm.
Okay, so the bigger the interval, the bigger the confidence.
Right. This what she's talking about, guys, right here. This number right here. I'm going to give these two different numbers. I'm going to give them vocabulary terms. The
Yes.
84 that we found right here, I'm going to call it a point estimate.
Okay.
And the reason we call it that is because that is just 1 point on the number line. That's 1 point where I think my true number of people who got an A is real close to that. I'm not sure if it's exactly right, but that's a good estimate. I believe because of this sample, I think that's a good point to estimate on my number line. Okay.
Okay.
And then the distance from here to here and the distance from here to here, or the 4 that I added, I'm going to call that, plus or minus, I'm going to call that my margin of error.
Yeah.
And the bigger this number gets, notice the bigger the interval gets. If I added 4 to both of them, I have a distance of 8 from the bottom end to the upper end. There's 8 spaces on the number line from here to here. But if I make my margin of error bigger, if I subtract 5 and add 5, subtract 10 and add 10, my margin of error, now I've got space of 20 spaces on my number line. My interval is larger, therefore my confidence is bigger. So as the margin of error gets bigger, the confidence directly gets bigger as well. The bigger my margin of error, the more confident I am. Let me ask you this. What if I had an interval that went from 0 all the way up to 500 in this example? Well, how many students do we have?
We have 500.
If I said that between 0 students and 500 students made an A, I'm 100% correct in that statement. Would you agree with that? Somewhere between 0 and 500 made an A. Would that be a true statement? Absolutely 100%. Well, 500 students took the test. Is that right?
Yes.
Now, we already know that 5 of them made an A out of the 30. But somewhere in between 0 students and 500 students, would you agree the true number of students that made an A is going to fall in that range somewhere, in that interval from 0 on this number line way out to 500? There's no way I could be wrong with that. Is that true?
Yes.
Okay. So I'm 100% confident in this statement, but how precise is that? Don't you already know that either 0 or to 500 people, somewhere, some number on the number line is how many people made A's out of that? So that doesn't help me any by guessing that interval.
Yeah.
So the smaller the interval, if I'm correct, I've got a better idea of how many truly made the A. So I want to know how many really made an A, and I want to estimate based on these 30 people, how many of these 500 really made an A. The bigger I make the interval by using this margin of error, the more likely I'm right, but the information is not helping me as much. It's kind of less precise, as you will. Okay?
Yeah.
So it's just kind of two things that battle each other in this thing. The confidence intervals. It's an interval from a lower bound to an upper bound. And the vocabulary term we're going to be using here is called a confidence interval. Okay? The confidence interval can be written 2 different ways. Can you see how I can write it this way, where I've got a point estimate and a margin of error? And then if I want to get it as interval form, in interval notation, I simply just subtract the margin of error, add the margin of error, and I have my lower bound of my interval and my upper bound of my interval. So I believe somewhere between those two, or here's a lower bound for the other interval and the upper bound. The reason we call them that is because, I mean, that's the lower number, and that's the higher number. You agree? I probably should have changed colors in here 10 times. This looks like a mess. I'm sorry about that. But that's the big idea with today's lesson. Okay?
Yeah.
But the mathematics of it is pretty simple. You take a point estimate, you find some point estimate from some. So by taking a sample, we can get a proportion. By using that proportion, we can go to a population and estimate, using that same proportion, a point estimate for the entire population. Yeah? And then we take that point estimate, and that might or might not be the right value. But if I give myself some range, some distance, lower bound, upper bound, the likelihood of having the true number of students that made an A out of that 500, I'm more likely to be right. The wider my interval, the more likely I am to contain the true number. That's statistics. That's called inference with statistics. Using a sample proportion to predict a population's true number or mean or proportion. And to have a better chance of being right, we create some interval to say we believe it's between here. I don't want to just pick one single point. I want to have a better chance of being right. So I'm going to give you some interval. The smaller the interval, the less confident, but the more precise. The bigger the interval, the more confident, but less precise, the less good information is given. Okay? That's the big picture with this whole idea of confidence intervals. So confidence intervals, this whole lesson built to a confidence interval. Inference with statistics.
Yeah.
We used a sample where we found 5 out of 30 or 16%, 16.7%, and we believe the population is going to have the same proportion, and we estimated how many students out of 500 made an A on the quiz, and we built an interval to have a better chance, a higher probability of having the true number of students within a range. That's today's lesson, guys.
Thank you, thank you, thank you.
You're welcome. You're welcome. You're welcome. Any other questions for today about taking the quiz? You should be, after today, you guys should be more than prepared for today's quiz. And this margin of error stuff, and this is really confidence intervals. This is how to build confidence intervals. That's on next week's. It's on next week's. So don't worry about it on today's quiz. That's not on there. Okay.
Right.
Yeah.
All right, guys. Well, I'm going to stop recording here. Let me stop that. I think we're all right.
Thank you.